Okay, let's get going here. It's just about noon. I want to give Gary the full time, plus give you guys a chance to ask some questions. Welcome to Moon 101, part 4 or 5? Part 5. Our speaker today is Gary Lofgren. Gary's going to talk about the crust. This is all of the different goals that the National Research Council and the NASA Advisory Council and various other august organizations have told us what to do, are concerned about the crust. So the lunar crust is a very interesting topic and one that is not entirely well. As I was telling some students the other day about, the moon's about as big as North America and South America combined, and if you were going to go to those places, you'd like to go like to Alaska and New Jersey and Mexico and the Andes. And I said, and it turns out, unbeknownst to us, we went to Iowa five or six times. So Gary's going to talk about that.
Thank you, Dean. That's who I am. I've did a lot of work with geologic training of the Apollo crews way back when I first came, and then I did a lot of science after that, and now I'm kind of playing around with the new stuff, new efforts to go back to the moon. Next slide. So what is the crust? Well, the crust, I will go through a series of slides and I will explain what the crust is, but the crust is basically the rocks, and the rocks are what we want and what we need to understand the crust. Okay, so the basic theme of the talk are what are rocks good for anyway, why do we want them, and what are they going to tell us? Next slide. So this is a slice through the moon, and I see from the schedule that I can't talk about this part. That's the next lecture. But really what I'm talking about is this part up here, the little thin crust, the skin on the peach. When we think about the Earth's analogy of a crust, it's the very outer surface of the planet. But it's what we see, it's what we can sample most readily, and it's the key to understanding what went on inside the planet, or it's one of the keys to understanding. Next slide. Our study of the moon brought this concept of a magma ocean to prominence. The magma ocean is something we can study on the moon, and we think we understand that reasonably well. It seems to be a fairly coherent idea. Fundamentally, it says that the outer surface of the planet, perhaps the outer 200 kilometers as much as, was totally molten at one very early point in the history of the moon. And then that began to solidify. And the evidence we see on the crust is the solidification of that huge body of magma that was on the outer side of the planet. And the simple-minded concept is that when you have a liquid and you crystallize minerals out of a liquid, the ones that are less dense than the fluid float up, and the ones that are more dense than the magma sink. And that's what this is meant to represent. We see the outer crust of the moon is mostly comprised of a mineral called anorthite, which is a calcium aluminum silicate. It's white, and therefore the crust is light colored. The other minerals that are common on the moon, the pyroxene and olefin, they sink down to some point where they reach neutral buoyancy or some solidification layer or whatever, and they begin to accumulate. Next slide. I apologize for the quality of the slide. It was the best I could get, but it kind of takes it a step beyond the previous two slides. This represents the completion of that crystallization of that upper crust. It's dominated by light-colored anorthite, but still has some of the other minerals in it. And then the stuff that sank became at least the upper part of the mantle, or some portion of the mantle we refer to it. So these are comprised of denser minerals that tend to sink in a liquid. And then there's this KREEP stuff that you'll hear about from time to time. It's all the stuff that didn't get incorporated into crystals very easily, get compressed into a thin layer between the two layers of things that are crystals. They're cations that are excluded. They're big cations, don't like going into crystals. That kind of stuff gets concentrated in the center. Then the next step is kind of where we are now, where we start having huge bombardment on the surface. The crust is broken up, pulverized is a better word. I'll get into this in more detail, but we have trouble finding pristine pieces of this crust. And as part of that process, lavas start to come up. We're getting melting down in this zone, and the basaltic lavas start coming to the surface, whether the lavas are triggered by heat in the center, heat of accretion from the early formation of the moon, or radioactive decay, or whether it's their impact generated, and it could be all three processes involved in getting these basaltic lavas to the surface. And they're an important part of the story. I'll just say right now, the rocks we collect in this zone tell us about probably about the first 500 to 600 million years of lunar history, the history of the planet. These basaltic rocks give us clues to what went on for the next billion years, or maybe a little more, as the planet, the inside of the planet was cooling down and you were bringing magmas to the surface. Next slide. This is what we can see when we look at the moon, and so we're seeing the crust, and the dark stuff are where the basaltic lavas dominate. They tend to be dark in color, and the light-colored stuff is dominated by that feldspar mineral, the calcium aluminum silicate. So that part of the moon is lighter. Showing the front and back side tells you that the front and back are very different places. I'm sure lots of you have seen these pictures before. And we just don't have the kinds of areas of lava. There's a few, but not very many on the backside. So there's a lot to learn about the crust, and perhaps a hint is going to the backside we might get more crustal samples. Next slide. Okay, so sitting on top of the crust, just for reference, you heard about the regolith the last time. The regolith is just pounded up crust at some depth, and we don't know what that depth is exactly because we've never had good information to tell us. But at some point you get into solid crust. But what we're sampling is this layer up here, which is basically the regolith and the broken up crust for the most part. So that's where we're getting our samples to try and piece together what we know about the crust. So just a little bit of context. Next slide. And this is a couple slides that kind of show the compositional differences between the front and the back. This is the front side. This is the area where most of the lavas or the dark areas are yellow on this slide. And this is a iron concentration of iron, and you can see it's an element that shows the compositional differences between the near side and the far side. And you can see there's great compositional differences. I mean, there are places on the front side of the moon that are kind of like the back side, but the back side appears to be somewhat unique in itself. So it definitely needs to be studied. Next slide. Okay, for all those simple concoctions of the crust, I throw this up, but this is probably more what the crust really looks like. It's not a nice little simple quick layers. It's probably all sorts of little small blobs of different composition magmas, and we have found lots of these different composition magmas in the crustal rocks we have found. And I just don't want you to get the idea that there's this huge, real simple model, that nature is much more complex. But we have no idea what this looks like in reality. This is just an artist's conception of a concept. And until we get more detailed kinds of data at depth, seismic data and things like that, we're not going to know the answers to those questions. Next slide. Okay, you saw Dean put up this priority from the this is from the National Research Council and National Academy of Science study. There's a couple others that come up with this very similar list. I use this one. This one talks about the crust specifically, and you saw all the subtopics that Dean listed. But if you look at the whole list of the top 8 priorities, the only 6 of those 8 priorities, all the one in yellow, require rocks to answer the questions. So, and even the regolith processes, while you're basically studying the regolith, the rocks are what's broken up to make the regolith. They're the starting material for the regolith, so you really got to know what the rocks are to understand the beginning of this process. So it's really only the lunar atmosphere and the volatiles of the lunar poles that don't require rocks. I mean, these require samples, but probably regolith samples, not rocks. But rocks are the answer to most of the important scientific questions that we're going to try and answer when we go back to the moon. Next slide. Okay, so what I want to do is talk a little bit about the rocks, and I'm going to show you some of the rocks we've collected and try and give you a picture of the kinds of rocks that we're looking for. Next slide. One of the common ones that we find easiest to collect, easiest to see, are the basaltic rocks. These are an eruption in Hawaii. This is some fire fountaining in Hawaii. Later you'll see why that's important. But these are volcanic processes that we've been able to observe. We know a lot about it on the Earth. And you look at a lava that we collect on the moon, and even to some geologists, they might not be able to distinguish a terrestrial lava from a lunar lava if you pick a terrestrial lava that hasn't been badly oxidized. So an experienced person could tell apart, and chemically they're very distinct. There's no mistake once you start doing the chemistry of these rocks. but just to look at the physical lava, they look very similar. Next slide. This is an example from an orbital photo of lava flows on the moon. These are out in the middle of the Embrium Basin. It's a 1,500 kilometer basin, Paul, something like that. 1,100 kilometer diameter basin. The Apollo 15 mission was at the southeastern corner of the Embrium Basin, right at the edge where they could get to the Apennine front or some of the crustal rocks as well as lavas. But we knew when we went there were lavas, and there were. Next slide. And when we got to 15, we went there because one of the things we wanted to look at was the rill. And this is the basaltic surface. And this is the only place where we've actually seen real outcrops. In the next slide, we'll actually see the outcrops. Next slide. Here, this is a 500 millimeter telephoto picture taken from the eastern side of the rill, looking across to the other side. And there's some definite lava flow exposed right here. This lava flow is between 6 and 8 meters, which is actually quite a large, very thick lava flow. And they tend, and looking at the size of the blocks in this rill and blocks we've seen elsewhere, the lavas do tend to be fairly thick flows. But there are some thin flows too. There are other pictures. There's a whole bunch of pictures that were taken, and there are some thin flows. I just didn't want to go into that level of detail. But I did want to show you there, and there's a real lavas underlying the surface of the mare, which is about here. Next slide. Okay, this is a basaltic lava collected at 15. It was picked up out on the mare. It's a highly vesicular, typical of the margins of a lava flow. These vesicles represent gas that must have been in the magma when it came to the surface. Mind you, coming to the surface of the moon, you're getting into a 10 to the minus 13 torr vacuum, so it doesn't take much gas to expand the lava. And we don't really know for sure what the gas is. We can only make an educated guess that it's probably carbon monoxide, because you're not going to get any oxidized gases up there, or we'd see evidence of it in the rocks, and we don't. In general, the rocks are very reduced. All the multivalent cations are in their reduced state, if not metallic, like we do have metallic iron, in small amounts of metallic iron. Next slide. This is a more typical basalt. It's a medium grained. You don't see the texture of it very well because this is a surface that has been continually bombarded by micrometeorites on the surface, and it's one kind of space weathering. There's a crust on here that's just from this constant bombardment. It develops a crust that's not, it's kind of hard to see through and see what the real rock looks like. You get these little impact pits from the micrometeorites hitting on here. They actually melt a little small. When I saw micrometeorites, I'm talking things that are millimeter, certainly less than a centimeter, and probably more millimeter size range, coming down and hitting this at about 20 to 30 kilometers per second. So it melts a little bit of the rock, and that's a common phenomenon on the surfaces of the rocks. Next slide. Inside the rock, and making a thin slice of it, looking at it in a microscope, you can see the different minerals. That's one common way of examining basalts and looking at them. This is an oxide mineral, ilmenite, and then the light-colored thing, low refractive index here is plagioclase, or anorthositic plagioclase, and then you've got olivine and pyroxene in there. The olivine is the highest refractive index, and the pyroxene is a slightly yellowish mineral. So those are the three major minerals in a basalt, or four if you count ilmenite. Next slide. This is just a little bit of data on this rock. This is the largest rock that was collected on Apollo 15. I'll say something about large rocks later. He picked it up. There was a requirement scientific requirement to gather some large rocks that were oriented with relative to what side was facing the sun, so they could study the effects of the sun on the rocks, solar implantation. So there was a reason to collect large rocks, and they collected a few. Been exposed on the surface for about 25 to 35 million years, but the rock was 3.3 billion years when it crystallized. Next slide. And here's a picture that shows a couple of different basalts. You can see that in this basalt, the vesicles aren't quite so round and regular. This is kind of typical. It gets on kind of vuggy as well as vesicular. Some of those vugs are formed because there's a volume change. When you crystallize something, the volume decreases relative to the liquid. And here's a more typical medium grain kind of basalt with the light colored mineral being feldspar and pyroxene and olivine in that rock. And that's more typical when you don't have that patina on there created by the constant impact of micrometeorites. Next slide. Okay, so basalts. All of the lunar rocks, one of the unique features of lunar rocks is because there's virtually no water, at least no water involved in the eruption and cooling and crystallization of these rocks on the surface. They're very, very fresh. There's no alteration. You don't find a terrestrial basalt that doesn't have some water in it and that some of the minerals haven't been altered by that little bit of water, even if it's a fraction of a percent. The lunar rocks are uniquely fresh, and you look at a thin slice of the surface, they're just pristine looking. Most of the basalts don't show significant shock effects. They haven't been blasted and pulverized like the earlier crust has. So you tend to get nice samples of basalts. They are clearly younger, and they're past the peak time of bombardment on the surface of the moon. These were erupted after that. Okay, next slide. Now, one feature that basalts have that's pretty much unique to basalt, but not totally, but when basalts come from deep in the earth and they're partial melts, they're the material that's been melted deep in the earth, and it leaves behind a concentration of olivine and pyroxene minerals that are the mantle that's not melted. And sometimes the lava will scoop up a little bit of that material. And this is an example of a lava collected in New Mexico. And these are what we refer to as ultramafic xenoliths. They're very olivine, pyroxene rich, almost no feldspar. They're really samples of the mantle of the Earth. Could be, we don't know the exact depth, could be a couple 300 kilometers deep. If we could find these kinds of things on the moon, they would be gold, because they would tell us something about definite things about the interior of the moon that we can only speculate about now. We can only model. On the Earth, we have these kinds of samples so that we can tell a lot more about them. So this is the kind of thing you tell astronauts to be on the lookout for. It's highly unlikely they'll find them, but if they do, you really want them. Next slide. Orange soil is technically a soil, but I like to refer to it as a rock because it is a piece of a magma, a volcanic magma. It tells us something about chemically about where it came from, and it's not something that was formed on the surface by impacts forming glass beads. These glass beads came from depth when they erupt in volcanic pyroclastic deposits, and so I like to think of them as our smallest rocks. We collected orange beads on 17, and we collected a green glass. Didn't get quite the notoriety when we collected it because we didn't realize what it was, but they've also are that same kind of thing, probably a pyroclastic deposit that came up from deep in the moon and tells us about the interior. Next slide. And here's the green glass spheres, and here's the orange glass spheres. These are microscope slides. These things are all less than a millimeter generally, between half a millimeter and a millimeter in diameter. But they have proved very valuable for understanding what kind of magmas are generated deep in the moon. So these are things that are important to find and interesting to look for. And we knew when we went to 17 that there was probably something like this. We had these dark mantles that were observed from orbit, and we suspected that they were probably the pyroclastic stuff, and they probably are, and this is probably a product of that. Next slide. Okay, we start talking about the crust. That's an entirely different matter. The crust, that crystallization of that magma ocean produced a very different kind of rock. If you want to make an analogy to a rock on Earth, it would be granite, i.e. in the modern words, countertop. You may recognize this is El Capitan at Yosemite. That's a 3,000-foot monolith of granite. It's a common thing on Earth, and we have all sorts of different compositions. The composition on the moon is not granite. It's a different composition, but it's the same basic concept. Next slide. And this is a piece of that anorthosite. This is got picked up on Apollo 15. It's one of the few pieces of pristine, unpulverized lunar crust. It's almost pure anorthite, pure calcium aluminum feldspar. This is just lunar soil, dirt on the outside. The rock is basically very white. Somewhere it picked up the moniker Genesis rock. That's what people refer to it. It's been a rock that's been difficult. It's important to date these rocks. This rock, however, is very difficult to date. The best way to date rocks is to have more than one mineral. 3 minerals would be nice. With a single point, you don't get as good a quantity of data. So far, the instruments have only been good enough to date the feldspar. There's a little bit of pyroxene in here, about 1 to 2% by volume, and instruments have gotten sensitive enough that we can probably analyze that small amount, and an effort is going on right now to do that. But this rock is clearly more than 4 billion years old, but we don't really know if it could be closer to 4.5 billion, which is closer to the age of the moon, but we don't know for sure. Some of the other rocks that we've collected, next slide, like this one, this was one of the other very few pieces of pristine lunar crust. It's got a weird sounding name, troctolite. All that means is it's this calcium aluminum feldspar mixed with a little bit of olivine, which is an iron magnesium silicate. And geologists are clever. They think of funny words to describe the ratios of these minerals one to another. So this one is a rock that's dominantly feldspar with up to 25% olivine, and that's basically what this is. The crystals are very coarse grained. It's basically unshocked. So again, it's one of the few pieces of pristine crust. This was found in a rake sample. It was a large rake sample. This is a centimeter, so it's several centimeters across, but it was not spotted on the surface. And I'll show you about rake samples a little bit more later. And I just want to point out the value. This was kind of like a blind sample, and I'll describe that process a little later. But it's a very important rock, and this is about 4.2 billion years old. They could date this accurately. Next slide. But most of the things we've dated come from rocks like this. And this is from Apollo 15. These are impact melt breccias. The black stuff in here was previously rock that was basically at ground zero for a big impact. Most of the rock at ground zero got melted. And then because of the turbulence of the event, unmelted fragments of the primitive crust got mixed in with it. But those fragments were thoroughly pulverized, granulated. It's hard to find a grain larger than a few microns in some of these, maybe up to a millimeter, but they're usually fairly well granulated. But they're still datable, and depending on whether they've been altered or not and how shock has affected the date, that adds a complications. But people have been able to come up with the best dates we have to date really come from these kinds of clasts that we find in these kinds of breccias. Next slide. This is just another example dealing with some pretty small pieces eventually. And anorite's another fancy name for a rock that doesn't have olivine. This is just feldspar and pyroxene. So don't get baffled by the names. There's basically 3 minerals on the moon, and the rocks are all variations of ratios of those 3 minerals, and we give fancy names to those ratios. Next slide. Okay, so the pristine crust. In general, these rocks crystallized at some depth. They're coarse-grained. Crystals generally larger than a centimeter. They can get up to an inch or several centimeters. Ages are going to range between 3.9 for the most part and 4.55 billion years, the very beginning of formation of the crust. They're fundamentally similar to crustal rocks on Earth, except that we just don't have any crustal rocks on Earth from that time period because they've all been destroyed by erosion and plate tectonics and things on the Earth, which makes the moon particularly valuable because it records that period in solar system history when the early planets, the early formation part of a planet. And that's one of the reasons the moon is so important. Unshocked samples, like I've said, pointed out many times, are very difficult to find, but very important to find them. And this is going to be one of the primary targets when we go back, is to find the best kinds of crust, primitive crust, and the most pristine primitive crust that we can find wherever we go. And we'll have to figure out strategies for doing that. And that's not easy. Next slide. They're volatiles. The moon is in general volatile depleted. Water being one of those volatiles that is
so they don't react?
Well, no, they're just not there. In the formation process of the moon, or the best theory we have today, which is the impact theory, with a Mars-sized planet impacting the Earth, with the debris from that impact forming the moon, a lot of certain elements were volatilized in that process. And that's probably too simple a statement, because the question of volatiles is complex. There's some volatiles that are still around that shouldn't be, if that was a simple answer. So the verdict is still out on that idea, but it does fit most of the data now, and it does kind of explain why certain elements like sodium and potassium, which are common on the Earth, all of these crustal rocks have a significant amounts of potassium and sodium, up to 3-4 weight percent. And the moon, we have less than 0.1% in general. It's around 0.1% or less, or slightly more. So the moon is significantly depleted in these, and it's characteristic. I mean, you wouldn't find terrestrial basalts depleted in these elements. You just wouldn't do it. But if you get a rock, a basalt that's depleted in these elements like this is, you'd know it's lunar. So it's a very distinctive chemical signature for the lavas. And for a lot of the crustal rocks, I mean, even the feldspar, the anorthite I'm talking about, has very little sodium in it. Anorthite minerals that crystallize on the Earth are typically almost 50-50, or maybe just slightly favoring the calcium end member. It's a solid solution series between sodium and calcium. And the typical anorthite rock on Earth has a feldspar that's about 65% of the calcium end member and about 35% of the sodium end member. So there's a lot of sodium in this same mineral on the Earth. And the sodium's just not there on the moon. The composition of the feldspar is maybe, for the anorthites, are maybe 2% of the sodium end member and 98% of the calcium end member. Some of the basaltic rocks might have as much as 10% of the sodium end member in the feldspar.
And again, what's the process that causes those to, I guess, what, leak essentially out of the environment?
Well, the idea was that during this initial impact, a lot of material was vaporized. A lot of material, the impacting body that hit the Earth was largely vaporized, and some of the Earth was vaporized, and that vapor, together with the debris from that impact, form a ring around the Earth. And that ring then reaccreted to form the moon. That's the simple-minded concept for that theory. And during that process, these elements were just vaporized away.
Okay.
So when the moon originally accreted, it didn't have them from the beginning.
Right, because they didn't survive the impact.
They didn't survive the impact. They vaporized away, and the vapor didn't recondense and become part of the moon. That's the simple-minded idea, and it fits most of the data. It's the working hypotheses at present for the origin of the moon.
Is that typical of other rocks created by impact events on Earth?
No. Rocks created by impact events are a much smaller event. It's not, you're not getting a Mars-sized planet hitting an Earth-sized planet, creating this huge vapor cloud. You're talking about an impact that's going to produce a crater and a cloud that's probably many times larger than a nuclear explosion, depending on the size of the impact, of course. But a large impact would create a vapor cloud, but gravity would tend to pull most of that stuff back down to Earth. So the stuff would reappear somewhere on the surface of the Earth. The vapor wouldn't leave Earth's gravity field. Now, on the moon, that might be a little different. Some of the stuff that's vaporized on the moon could actually go off into space, but we don't have a way to measure that very well, because our idea of ground zero is not that solid. We know what it is today, but we don't know exactly what it was in the beginning. Okay, next slide. And this is just a quick slide to show you the difference in the ages, the range of ages for mare basalts. Some of the oldest mare basalts do get up above 4 billion years, but these are rather uncommon basalts and are peculiar to one particular site. Most of the other lavas are less than 4 billion years and range all the way down to about 3 billion years, and there's one lunar meteorite that sits down here a little bit below. But we have evidence based on orbital data, crater counting, compositional data from orbit that lavas probably could get as young as 2 billion years on the western limb of the near side, the far western edge of Oceanus Procellarum. We could have lavas there as young as 2 billion, certainly 2.5 billion. That's what we really want to know. The crater count suggests some much younger lavas over there, but we don't really know until we get some ground truth what the ages really are. And this is the variety of suites of rocks from the original crust. These are just some fancy names again that geologists give to indicate some of the compositional variations. But you can see these rocks tend to be all in essence greater than 4 billion years, going back to the original formation age of the moon. And there appears to be some compositional effect on the age, but these are highly damaged rocks, so it's hard to be totally confident in that, but there's a body of data building up that suggests that. This is the kind of data where we need much more information from rocks that haven't been so battered by impact. That would really be nice. Next slide. Okay, I want to talk a little bit about impact-generated rocks. Before we went to the moon, we didn't really know much about impacts or impact processes. Only a few craters had been identified as impact rocks on the surface of the Earth. We didn't really understand what impact breccias were, impact melt rocks. We hadn't really grasped that concept. Geologists had been mapping these kinds of rocks for lots of years and not really knowing what they were, having trouble putting them in context. And this is a picture of Meteor Crater to emphasize that. I know Gene Shoemaker solidified the idea that this was in fact an impact-generated crater in the mid-60s. I mean, people suspected that earlier, but he was the one that proved it beyond all doubt. So when we went to the moon, we didn't understand that so much, and consequently we thought that many of the craters you see on the moon were volcanic, or we thought a high percentage of them were. Some people did. Some people weren't so sure. That was a controversial topic. Now we know that the vast majority of craters on the surface of the moon are impact craters. There are some volcanic craters, but they're clearly in the minority. We think we can identify those now with more careful study, but far and away, the impact rocks are the dominant thing, and they really influence what the surface of the moon looks like and the kinds of rocks that you can collect and how we can study it. So it's important to know what impact rocks are and what they look like and as much about them as we can. So studying these rocks as they started to come back from the moon has been a real educational experience for geologists, and in the process of doing that, we've learned how to identify many more craters on Earth, and now the inventory of large craters gets well over a couple hundred, significant sized craters, and craters that do serious damage to the Earth. And so this process is not that uncommon, although most of these big craters are in older rocks, thank heaven. But it's going to happen again someday, but we just hope it doesn't happen in the next few hundred years. Next slide. These are typical breccias, and a breccia is a term we use to describe rocks on Earth that aren't necessarily formed by impact. All breccia means is you've got a random collection of fragments that are somehow glued together into a rock, and how you get that collection of fragments can have many processes. On Earth there's a lot of processes that do that. Earthquakes can do it. All kinds of different ash flow deposits and things like that produce breccias. On the moon, however, when you see a breccia, the chances are very high that it was formed by an impact, and that this is the product of a very energetic impact on the surface. And if you think of an impact, a large impact, the impacting body hits the moon at a much higher speed than impacting bodies hit the Earth, because the moon has no atmosphere. So they can hit it as fast as 30 kilometers per second, many, many times the speed of a bullet. That's an incredibly energetic process. A large amount of material at ground zero will be melted, and then a lot of broken up debris will be generated, which will be thrown out, mixed together with this melted material. And that's what we find in most of these rocks. Lots of times this fine-grained material. these rocks don't have, these particular breccias don't have a lot of impact melt, just a small amount sort of gluing them together and lots of class in them. This rock has been the subject of extensive study. We've made several slabs of it. Scientists go in and look at these slabs and pick out interesting little kernels of pristine lunar crust to study. And again, that's one of the ways we find it. I showed you those other two impact melt breccias before. So these, and some of them, you can see most of the rocks look pretty similar. And sometimes a breccia like this will only be 2 or 3 components. And sometimes you can identify 10, 20 different components. So it's a variable process. Next slide. Now here's an example of an impact melt rock. This would be a rock from basically ground zero that did not get mixed up with other class, and is basically just the melt that is subsequently crystallized. In some sense, this process is the same as the crystallization of a basaltic lava, except that the melt wasn't formed by a lava, and the impacting body, which is largely vaporized in this process because the impact velocity is so high, there's always a chemical signature remaining in these rocks. While we don't see pieces of the impacting body, there's a chemical imprint that's put on these rocks that clearly distinguishes them as impact-generated rocks. And typically it's the group of what they call the platinum group elements, platinum, gold, uridium, palladium, etc., that are enriched in these lavas over the intrinsic values of those elements on the moon, because meteorites are enriched in those elements. It's this, the same concept is used on the Earth to identify impact melts. So this is an important kind of sample to collect, because this kind of sample crystallizes like any magma, and the crystallization age will reflect the age of the melt when it was formed, and theoretically the age of that crater when that crater was formed, if you can put the rock together with the crater. And that's the trick in lunar geology. When you collect one of these things, is knowing which cratering event it dates. And so that's one of the puzzles that the scientists are always trying to unravel when they study these kinds of rocks and they date them. What impact event are they dating? And the more of these kinds of samples we get, the better idea we'll have. But in general, these impact melts tend to be older than 4 billion years or 3.8 billion years and older. And they generally are pieces of the original crust, or are largely pieces of the original crust. You may get a little bit of the lava, the basaltic lava, mixed in with that at some point. Because when these big things hit and they melt everything at ground zero, they melt everything. And that kind of stuff, the natural processes on the surface of the moon mix up a lot of this stuff together, because while one of those impacts may melt a lot of stuff here, a lot of small fragments get thrown away kilometers away, or tens of kilometers, or hundreds of kilometers, and fall farther away as discrete chunks. They didn't get melted. They're discrete chunks of rock that get thrown long distances. So you don't always know where these chunks come from. And that's not an easy thing to reconstruct, because there's many, many craters that these things could be related to. So that's part of the real detective story. Next slide. Okay, so melt rocks are basically fine-grained, uniform, crystallized melt, like I said, with that chemical signature, and they're excellent for age dating. The breccias are not much good for age dating, because you've got all sorts of fragments mixed in there. Fragments in those breccias can have different dates from when they formed, and the cratering event that formed the breccias do not reset the ages. When you totally melt something and crystallize it, you reset the crystallization age. When you just heat something up a little bit, you may affect that age a little bit, make it hard to determine, but you don't change it fundamentally. And the date in those fragments in a breccia aren't really dating the event that formed it. They're from some previous event, and who knows where those fragments came from. And that's the real problem. But they are important for finding bits of the pristine crust, because they do get incorporated in these breccias because of the process I just described, where this stuff gets thrown around heterogeneously and mixed together. And if you can find pieces of the pristine crust, while you don't know exactly where it came from, if you know it's part of the pristine crust, you know that's what you're dating. You know what the chemical signature of that rock is telling you. So that's an important source for finding those kinds of rocks, for pristine crustal rocks. Next slide. Another good kind of sample are the rake samples we collected. Those were something that was they started doing later in the missions. We first did it effectively on 15. We understood that we could find rocks in this size range, or even better in this size range, or even slightly larger, maybe 10 to 20 millimeters. And these is plenty of material for a scientist to age date it and study it. And if you collect these kinds of rocks, you can get many, many more rocks to look at. And these rocks that have come from all sorts of different places, so you get more variety than when you collect the big pieces. Next slide. And this is a rake sample being collected. It's a special kind of rake. The tines were set a centimeter apart, so you were collecting everything larger than a centimeter. And you would sit and you would rake that through the top 6 or 8 or 10 centimeters of the surface, looking for collecting these rocks. And I think that's Jack actually doing that on Apollo 17. I don't remember for sure. But these samples have proven very useful, and that troctolite that I showed you came from a sample collected in this manner. So I think this is an important kind of sample to continue to think about collecting on the surface. It's a blind sample. You don't know what you're getting. Everything's so covered with dust that you can't identify it until you get it back in the laboratory and you can get all that dust off of it. Nobody recognized that trocolite as the beautiful rock it was until they got in there and blew all the dust off of it. And eureka, they had a gorgeous sample. The dust just gets on everything and sticks to it. And when you're pulling these things out of the regolith, they're going to be totally dust covered. So you just collect them, put them in a bag, and bring them home, and then you do what you can with them. And some of them are monotonously repetitive, and some of them are really good. You're looking for the nuggets. Next slide. I throw this up just to give you a feeling for increased analytical technique. This is one of the guys that works at NASA, Larry Nyquist, in his lab, doing neodymium samarium. He took this little clast, this is a millimeter, so this was a little over a millimeter, and analyzed things out to this kind of accuracy here to get, this is what the sample weighed, and this is the amount of neodymium he was measuring to determine the neodymium ratio in this rock and get information about that rock. So it just, with the increasing quality of instruments, we can deal with smaller and smaller pieces of rock. So that's why collecting these smaller rocks is really useful and is important. Next slide. Okay, where do we find the rocks? Well, rocks are everywhere on the moon. But you look at this scene. This is up on Hadley Delta, not far from where they found the Genesis rock. But you don't see a lot of rocks on the surface. There weren't very many. Maybe that's one of the reasons he found the Genesis rock so easily, is because it was standing up there like on a little pedestal, waiting for him to come collect it. And there weren't many rocks around. The next slide shows a more typical mare. This was near Dune Crater, south of the Lem, between Station 7 there and where the Lem was, but typical mare. There's a lot of rocks out there. The problem is, which ones do you get? And that's always going to be the dilemma. And having guys up there who can discriminate which rocks are good ones and which ones are bad ones, by eyeball is really good, but if we had some instrumental assistance, and I think we can, by the time we go back, have some sophisticated instruments that would actually give us a little bit more information, allowing us to collect more intelligently. Next slide. And then you get to areas like, this is along the edge of Hadley Rill. You can see, and this is sort of on the near side where they were standing from, and collecting, and this is kind of almost outcrop here. Maybe it is outcrop that's been slightly moved around, but it's basically part of a basaltic layer. That's a lot of rock. And then this next one is an impact crater into the mare not far from the rill. With all that basalt underneath and everything, you would expect to find basalt in this crater, but you don't. This is some breccias. And here's a crater that's almost solid rocks, very fresh young crater, not very deep. And so there's obviously a layer of impact breccias on top of those layers of basalt at the Apollo 15 site. Everybody would have expected that to be basalt, but the couple samples they got were not. Now, maybe they didn't collect the right samples, but the couple that they got were not. Next slide. And then here's a crater. This is North Ray Crater in Apollo 16. You don't get to these samples. They couldn't get close enough to the rim to actually see the bottom of that crater was pretty deep. But you do find rocks around the edges of craters, and that obviously is an important place to find them. Next slide. And here's another place I think it's important to get rocks. When you find big boulders, the next best thing, to a geologist, an outcrop is gold. An outcrop is rocks that are where they were put by nature, and you know exactly the context. You know the formation context. Most of the rocks we collect on the moon, we don't know the context in which they formed. We can guess. We know lava is crystallized in lava flows. We know impact breccias came from a crater, but we don't really know the relationship of one rock to another. When you find big boulders like this, however, you can find multiple relations. And this was collected on Apollo 17. Here's a dike of impact melt running through this plagioclase pyroxene rock. They were able to collect a piece of this and a piece of this and a piece of this other rock, which is sort of where this came from, and determine the age relationships between these samples. He was fortunate, though, to get these samples, because some of these rocks are pretty hard and you're whacking at them with a hammer. It's not so easy to get the exact sample you want. So one of the things we need to think about is how can people sample these kinds of big boulders and get precisely the sample you want. The obvious way people do it on Earth is with a chainsaw type device that has a drill core at the end of it, and they actually drill a little core into the rock and they can get a piece right where they want it. Something like that would be nice.
Gary, what is the tool that he's using there?
That is the tongs, and he's using that tongs not to do anything but to gauge the distance between his camera lens and the rock. We devised a way for guys to take close-ups. It was not easy because they didn't have a viewfinder. They had no way to focus their lens. When they were taking close-ups, that was particularly difficult. We tried those in training in the field, and they never could get it right. So we put a little mark on that tong. So you put the tong on the rock and lined the front of the lens up with the mark. You knew it was going to be in focus. So that's why that's there. It's not doing anything with it except using it as a focal distance to the rock. Okay, next slide. Okay, so a few lessons from Apollo, and here I'll pontificate as an ex-trainer, field geologist, curator, whatever else you can call me. But and these are my opinions, may not be shared by everybody, but basalts and fine-grained melt rocks, we don't need very big samples anymore. You know, a golf ball to baseball size rock is plenty big. And that's one of the things we're going to have to do. We're going to figure out ways to break up rocks easily or whatever to bring them back. Certainly half a kilogram or even less. These are very uniform rocks. 10 grams can, 100 scientists can work on 10 grams. So that's become obvious. Collect all of these you can find. These are important. The problem's going to be recognizing them, and they're rare. So they always got to be on the lookout. And then the breccias now, on the other hand, we may want to collect some large breccias. What we've got to do is get clever about which ones are the important ones to bring back. And they're going to be the ones that show the most variation. So the guys collecting in the field have to learn how to recognize that there's a variety of class in this breccia, not just a single kind, or a monolithic breccia, is would be the technical term, versus a multilithic breccia. So those are the kinds of things we need to start telling them. I think rake samples are very important, and I think we need fewer of these. The soil isn't that complicated. The soil's totally churned up. We don't need that much of it to understand the process. We don't need as much as we collected on Apollo, and we certainly don't want to put soil in the same bags with rocks. We know how that makes it very difficult to ever get the rocks clean again. So it's important to have this kind of material. It's important to go down, maybe do a deep drill down into this, to the regolith, but it's not important to collect a soil sample every time you collect a rock like we did on Apollo, virtually. Next slide. Okay. Here's another important issue, and I'm really putting on my curator's hat here. Certain things happened on Apollo. Honest mistakes. But when we created the seals on the rock boxes, they used indium silver alloy. It's soft. You can put a metal edge into it and help seal it. but that eliminated a whole group of chemical elements that the scientists could analyze for. And they didn't like that. We need to find better materials. We need to be very conscious of what materials we use for that kind of thing. This was a real mistake, and they knew better than this. This is not monitoring the process well enough. We knew lead is absolutely verboten. We don't want lead to get into anything. Lead is, it just moves around ubiquitously. You can get it about so soft you can rub it on your fingers, you can put it anywhere else. But to actually treat the drill core with lead, and that's the process that, the manufacturing process of the day, that's the way it was done. Nobody was monitoring the process closely enough to make sure it didn't happen. And that's the problem with what we do. When we, the edict is, curation begins now when you start conceiving of containers, conceiving of tools, and how you're going to collect samples. That's when it's important. That's when you define the materials that are going to come in contact with the sample. That's when you got to be smart. And then you got to watch this manufacturing process like a zealot all the way through to make sure this kind of thing doesn't happen. The guy that did it was just doing it the way he always did it. Nobody told him not to.
You're talking about watching the manufacturing process here, but thinking like a systems engineer, how do you bring the curation issues back upwards to design to make sure that stuff like that doesn't
Well, that's where we got to be talking to each other. One of the major findings of that National Science Academy study that I mentioned, where I put those 8 priorities on at the beginning, Dean had the reference to it on his list. One of the findings is that they want a body of scientists to look at what we did in curation, what was done during Apollo, and to see how things have changed. Maybe there are elements now that are even more important to scientists than some that we thought of back then. So the Academy has charged the science community with looking at the issue of contamination all over again and producing a document that defines what are contamination issues and are not, what collection techniques we want to use, and then it's important to communicate that information to the people who are building the hardware. And that's the step that has to happen. And guys like me are going to have to try and make it happen and stay in communication. But the communication loop has to be open. You know, it has to be there. Guys like Dean help it to be there.
We hope.
So we hope, yeah. So anyway, you know, I think you know, we had those beautiful rock boxes during Apollo. I'm not sure that we need to use rock boxes to bring back samples. I think we can seal rocks well enough in bags and not have to have real fancy containers. Rocks are their own best container. You can chip away the outer centimeter of a rock and you can get right down to very pristine material again. So I think that we need to look at the whole sample storage, sample collection issues all over again. And that's going to be an important part of what goes on in the next couple of 3 years. That's all I have to say.
Any questions? We got about 5 minutes.
What did the Indian seals do that you didn't like?
Well, indium was an important element for. It was an important indicator of meteoritic contamination. It was an important indicator of other things, and so it contaminates the samples because it's so soft. It's like lead. It's even softer than lead, so it just goes everywhere. And so he couldn't be sure that he wasn't measuring the indium from the seals when he was doing a rock, and so it just kind of he lost that element, which is an important element for him and the kinds of studies he did. And he just didn't know they were doing that. You know, it was just lack of communication. That's the kind of communication we need to have in the future.